and I know how busy Brian is, to introduce Mr. Brian Patterson. And we've been talking through Grid Former. This is an organization of sort of forward-looking little startups, people who have niche technologies and they want them to get on the system. So that's how I got to know Brian, and I've learned a lot from him. So I thought maybe we should have a seminar and hear more of his thinking. He's been very active in, as he'll tell us, in eMERGE Alliance. So Brian, it's all yours. Okay. Thank you.
And we'll touch on the eMERGE at the end of this, but why don't we get right into it and say that this is a little bit more of almost a journalistic approach to this whole subject of electricity and where we're going. Than it is science or scientific, but it includes hopefully a useful amount of science that will be interesting to everyone. One of the things that we started looking at in the early days of eMERGE was this sort of nexus of all the technologies that are intersecting almost simultaneously, and looking back in history of how things come into being in a new way, particularly in the technical or scientific arena. It's often multiple disciplines that come together simultaneously that change the shape of the traditional S-curve of adoption. And when we reflect on all the things that are impacting potentially impacting the technology of energy and particularly electricity, it's a long list, and it's really almost all of these areas are incredibly active right now in terms of innovation and development. So what that leads to, of course, for some, it may look chaotic. It's very disruptive. There's a lot of things going on. It's sometimes hard to follow them all, et cetera, impacting business and people's careers and knowledge bases and so on. But it also presents opportunity, and that's literally the difference between being confused and taking advantage. Even if you don't see the entire picture, there's still tons of opportunity that come along with disruption. So part of my job, and in fact, my last job before I quote unquote retired, was a futurist for a corporation, happened to be Armstrong World Industries. And I got the title of futurist because I was largely responsible for being provocative about what might be happening in the future. And I found my job relatively simple because I always told people that all I had to do was keep an eye on the inevitable. The difficulty in future telling is an issue of timing more than it is of direction. And you can get very scientific about plotting technology curves and things like that and intersections, which I did to make some guesstimates at timing. But keeping an eye on the inevitable is one important aspect of telling the future. And my background was in interconnection, spent most of my life in telecommunications and computer electronics and automotive electronics, but switched toward the end of my career to looking at electricity. And I was quite shocked, actually, that the electricity world seemed to be way behind from a technology standpoint from the world that I was coming from, which was computing, fiber optics, and information transmission, and so on. But this whole idea of the inevitable is pretty straightforward. Most people don't doubt that there's an inevitability to our own existence. But you have to look at other things that are going on, and to look at electricity, for example, and borrowing a bit from Ben Franklin's experience with the key and the kite. You can make predictions maybe in the future that there is an inevitable desire to somehow harness the energy that comes from our atmosphere, or that is trapped in our atmosphere and sometimes gets released, the lightning bolts. And I would, when I looked at this, I said, wow, a single bolt of lightning is pretty significant, about 5 billion joules of energy. And I kind of did a quick translation to say, well, that's a lot of using a 1,000-watt toaster, which is what I have in my kitchen here. It's about 84,000 minutes of toasting. I know these are kind of abstract comparisons, but but easily, another easy metric would be one bolt of lightning could power a significant number of homes. I think I came up with something in the area of maybe 50 homes or so for a day. So lightning bolts strike the earth, every second, about 8 million a day, 3 billion strikes per year around the world. Are pretty interesting and provocative about thinking how could we harness that amount of electricity that's much more electricity than most of the power plants can produce. So my prediction as a result of that, just to let you know, and I don't think this is really too crazy, but I think we're going to be harvesting directly atmospheric energy probably later in this century. Now, I'm not the first to think of that. Our good friend Nikola Tesla, and as I said, Ben Franklin looked at what was going on in the atmosphere. But even the most recent are people working with graphene and trying to find a way to capture that lightning and make it useful. But there are a lot of other obvious inevitables that are going on. Our buildings, we were just talking to Dan about the building he's in, are going from passive to electroactive, meaning that electricity is doing work and modifying our environment dynamically as we go along. So that's an inevitable thing, is that we're going to use more electricity to provide what I call electroactive environments for our existence. We're also going from things that were kind of dumb, you have to turn a switch on to manipulate the power, to things that are automatic. My home is mostly automated through the help of Google and Alexa and all the rest of them, smart things and so on. I have quite a combination of what I think is just scratching the surface of smart control of my home and my environment. In the electrical world, in particular, we're really starting to integrate that capability to do work in a very direct way into buildings, whether they're in our homes, pictured on the right there, bottom, or that's the Geophysical Union in Washington, D.C. At the top right, which is now, by the way, all D.C. Work environment with the solar roof and so on and so forth. And I noticed even the DOE has a request out for people who are interested in built-in photovoltaics to try to accelerate that part of the market. But another obvious one, and I call this the killer app, is to go from combustion engine to electric motor transportation, propulsion. And this is a huge one because of the amount of, if you do the conversions of petrochemical fuel that's used in automobiles, buses, trains, and cars, and planes, it's a huge amount of electricity ultimately needed. What's neat about this is Einstein really, I think he understood this very directly, that energy is used to organize matter, meaning to transform it in some way, to make it from less useful to more useful. But you need information to get the proper application of that transformation, to do it in the right way to get the most value out of it. And this is where I get excited about, and I'm sure you all are, is excited about how information is going to help us in this new age of electricity and energy. But sadly, the problem is that all that information that we have now and capability, without the ability to act on it, in other words, to articulate, some people would say manipulate, but I'll say articulate the energy, the electricity in particular, into its most useful conduct. And electricity is probably one of the most useful forms of energy, at least practical in at this time. So making that marriage between information, which will guide this transformation of matter, or work as we call it, into more and more useful capability, is really the exciting part. Now we have this big machine called the grid. People still call it, surprisingly, the world's largest man-made machine. I disagree. That I think it's been overtaken by the internet, and I think the internet now is, at least temporarily, the largest man-made machine in its ability to exchange information. And if we actually do a comparison of what has gone on in information systems since I was born, and yeah, that was my sort of benchmark to start when I was born, when the transistor was invented, about the same time, although I think there's a debate between 1946 and 47. But in any case, from that time to the time that we had personal computers and things was about 30 years. To get to the same point, and I call this today, barely we're at the beginning of what you might call the analogous representation of a personal computer and a personal power system, and most of that's the small solar storage systems that go on homes or in some cases buildings. But we're really just getting to where we were in 1975 with the beginning of the personal computer revolution. But if you carry that forward and look at, is there a way to catch up, so to speak? And you look at how we went from the personal computer to essentially the internet, a worldwide network that really provided enormous value to each node in the system, the personal computer or personal device, we should say, probably today. We need to make that same transition, even though we're at the beginning of building these little, what you would call personal power systems or nanogrids, to get to a true international energy network, which would then perhaps again overtake or at least marry with the significance of the internet. So that's kind of the vision that sticks in many of our minds. And as we talk to people, we find out more and more people have this very similar vision that that's where we need to get to with energy. So the question is, how do we get there? How fast can we get there? How can we transform the grid into to bring it into this new age of electricity, which will provide enormous value for man's existence on Earth? And that's part of that needs to be part of that needs to be, of course, distributed and equally distributed around the world in places that are less developed than they were today. Now, you can kind of say, well, no kidding, this is what we need to do. We need to have a distributed, integrated, largely renewable resource, hopefully semi-autonomously transacted, because there's going to be a gazillion transactions that need to be accomplished simultaneously, and man as a human interface can't do it that fast or that comprehensively. So we need a semi-autonomous capability, with probably the artificial intelligence being a big piece of it. But I think all that's inevitable, and a lot of people would say, no kidding, Dick Tracy, that's an easy prediction to make. How do you get there, though? Well, first of all, we look at the drivers. What's driving all this? And I think we know the big three, as I call it, the D3: decarbonization, decentralization, and we can talk about the significance of decentralization, but even if we don't fully appreciate why it should be decentralized, we certainly say that the internet is a product of decentralization. And last but not least is digitalization. Now, I'm going to talk about two types of digitalization. One is this information, the coupling of information with this ubiquitous energy network. But the other is maybe the electricity itself should be digital. And so if we act on those drivers in a forceful way, they can result in major environmental and economic improvements around the world and for all of its population. Now, at one time, and just to bring back the analogy, we transformed analog telephony into a digital information production and exchange. I believe we need to mirror this, as many do, with electric energy, as suggested by Einstein. Really, remembering that it takes energy to organize matter, and that should be guided by the best information available in a timely way. So Here's what it looks like. We're going to go. We think we're going to go from the centrally fed serial connectivity of our 100-year-old power grid to a mesh network connectivity, or grid of grids, as I like to call it. People objected when I called it the network of energy because they said, "Oh, that's an information term. It'll confuse people." But that's neither here nor there. So we will just keep calling it a grid, but it is a grid of grids now. Because each of the analogy again with a central computer or the central power plant is now going to be transformed as a personal computer. Got transformed into decentralized nodes. So a little bit more on this obvious result is that when you have this distributed capability, whether it's information or energy production and storage and buffering and so on, let's call those things microgrids as opposed to personal power systems. And you put them in a network, their value is almost exponentially increased, by the number of connected microgrids in the network. Even though the cost of each microgrid may seem initially a little bit high, I'm sure the people that had the first personal computers thought that was a pretty darn expensive typewriter too. But as you add apps, as we did in information, as we add capability of using electricity in new and unique ways, the idea of putting them into a network will accrue that sort of exponential value proposition. It might sound kind of insane to say, well, we're going to have a grid of grids like we have the internet around the world that's going to couple continents. In fact, the whole globe, and I believe it goes further than that. We'll definitely couple anything we do in outer space, probably the moon first. I know we're probably going to try to settle the moon a little bit and see what that's like, sort of as a campground for finding other places that human existence can thrive. So I believe that they will all be coupled into this kind of exchange of both information and energy. Now, one of the interesting things is that we've already started that this link between, I don't know how many people are familiar with the Sun cable, but it runs from Australia to Singapore, underground ocean cable, high voltage DC, 10 gigawatt capacity solar farm connected to the end terminal with about 22 gigawatt hours of battery storage to buffer that exchange. And it's amazing because Australia at the same time is one of the largest fossil fuels exporter, but is now going to export solar energy. So the production of energy at the beginning of the Sun cable is solar, not the fossil fuel generation that is typical around the world. So I believe that this infrastructure will facilitate and support large-scale economic development in places that don't have that energy. And it's analogous to the pipelines that we've started to use for natural gas and petroleum, but now we can move electricity in the same way, pretty efficiently, much less expensively in energy per dollar spent, if you will. So we can kind of project that and predict that. For example, I think Africa probably within a decade or two will start to be a major exporter of energy, and most people would not think of it that way, but it is an ideal location, has an ideal position in the globe, being nearer to the equator and having great solar exposure, and kind of centrally located too. To the continents, the rest of the continents around it. So, what is that grid of grids going to really look like? Well, first of all, I believe that most of the new capacity that we're going to put into the system is going to be generated at the fringe. As you probably know, 80% of the information that flows on the internet now is created on cell phones and personal computers, not at mainframes and so on. The preponderance of new generation, I believe, will involve natively direct current technology, not alternating current. And it's not going to come from rotating, generation. which is what the AC was best at. It's going to employ an extensive use of non-synchronous, I believe, non-synchronous DC coupling. The complexity of AC coupling of different systems and storage and so on is just, to me, mind-boggling and expensive, and puts a big overhead of complexity and expense on the system that doesn't belong there. I believe it's going to be a mesh network so that there's peer-to-peer transaction as well as hierarchical flows, and that mesh will provide a sort of a self-healing or self-configuring topology that will allow these dynamic needs like isolating failures and threats and so on and so forth to be easily handled, pretty much as the internet has so far, at least. I don't know. Hopefully, it's going to continue to be able to do that. I believe that this semi-autonomous distributed, and I should have advanced the slide here, semi-autonomous distributed control will be achieved through a tiered transactional management, aided on the physics side and electricity a lot by droop control, meaning the simplicity of monitoring voltage will be a major factor there, but as well now allow the incorporation of policy into power flow. And that is a really a very crude thing that we do today, but with an advanced grid and an advanced semi-autonomous or automated control systems, we should be able to achieve policy right down to the individual level. It's just like me deciding how bright my screen is going to be or how much memory I want to allocate to something or whatever. I have all that capability on my computer. I don't have much of that, if any, on my power system. And finally, that the local microgrid versatility will evolve as energy as a service. And again, the parallel there with computing is that how many people now are in a business because they have computing capability. They can run businesses, whether it's trading businesses or other services from a computer without brick and mortar and so on. And I believe the energy is going to be very similar. And there will be differentiation capability in the semi-autonomous way of controlling things that will yield new business models for anybody who's dealing in electric power. And when I say anybody, that means possibly anybody, meaning today anybody can get onto a computer and start a business if they're wise enough and knowledgeable enough to know what to do there. So a couple of last things. What that hopefully will do is convert our current methodology of valuing electricity as a kilowatt commodity over to a service value. And the service value then can be proportionate to what the energy is doing as opposed to what it costs to create it. Last but not least, and this is where I stretch out a little bit more than some on the subject of digital, I believe that today we have analog form of electricity, basically AC, and we try to make it sort of controlled by digital electronics, but it's pretty difficult to do because it is it's a moving target, so to speak. It's a moving waveform. It has lots of elements of difficulty in phase matching and power factor correction and harmonics and all kinds of things. So I think that can be simplified largely by DC, but beyond that, if we go to a digital form, whether that's a pulsed or a semi-modulated, digitally modulated power on the DC transmission, that we will change electricity and make it so much more capable than dealing with the AC complexity issue. Whoops. So that's kind of, and it may be obvious to some, but when I talk to a lot of people, they say, wow, I never thought of it that way. But I'm happy to report that the more and more people I talk to, that many people see parts or the whole of what I just said as being where we're going or where we're likely to go with electricity. So what's the chance of these predictions, if you will, if you want to call them predictions? Maybe they're pretty obvious, but what's the chance that they'll come true? Well, you look for evidence as to what things are doing. One of the pieces of evidence, we happen to have a member in Emerge that's a utility, and they have a division which is a non-regulated division called Amera Technologies. The utility is called Amera. They're actually Canadian and Nova Scotia, but they have territories in the United States and in the Caribbean. And they have started down this path, probably a little bit further along than most folks that I've seen. So what they envision is this multi-tier kind of smart network, if you will. Their vision of it largely right now is what we call in front of the meter, right? Which means it's in currently what's defined as a utility domain, but it is basically a DC coupled grid transmitting DC at low and potentially medium voltages. Most of this exists, between a substation and an end user. And it connects back into the traditional grid. It is all bidirectional, which is relatively simple to do, or much easier to do with DC than AC, because you don't have to synchronize in both directions and all that. So everything from coupling and black starts and instantaneous loads and things like that are more easily handled. So they went to DC coupling. If you follow this chart, and I know it's a bit of an eye chart, but you go all the way over to the left where you see the little car there and the feed that's going into that building, and there could be a home there or what have you. You see that it converts, and it can either feed into the building DC or AC. But this is a non-synchronous grid, okay? So and it's bidirectional, and the assets of generation, storage, etc., can be supplemented in what we call community kind of situation, whether it's community solar, community wind, maybe it's fuel cells, maybe it's a small atomic reactor, nuclear energy, or storage, that can be coupled in at various points, pretty much like you would couple in maybe a hard drive or a local service provider into the internet to provide storage capability. And then of course you can tier this out, or service different kind of subnetworks in this network. You could divide it out, I think, as in part they do, into residential, commercial, and then what we call municipal and critical services. And maybe you could have another section that would even be called national security, which would be military and home what do we call it? The home. I'm losing my thought here, but the home defense or whatever it's called, the custom services and things like that. But however you configure it just is sort of like little local area networks or metro area networks and so on and so forth that you couple together. Again, where the coupling largely is DC. Now, we don't want to strand the AC assets we have. We have tremendous investment in this formerly largest machine, I'll say. So we need to pay attention to how do we couple that in, and there'll be neighborhoods. This would almost assume that there'd be greenfield neighborhoods, new developments and new business parks and new factories and things. But we have this tremendous, built environment. So most of the new energy is going to have to go into existing built environment. And so we have to consider the hybrid nature of the AC and DC. So again, where we have new things coming in, we should have parallel capability. And one of the ways to get that, for example, a simple one, is to have start to build our appliances so that they can either be fed DC or AC. So that way, as we make the transition and DC power becomes available from one of these more articulated and capable grids, local grids, that it can be enjoyed by, in homes and buildings without the need to strand the assets of previous investments. And same thing goes with the grid. There's lots we can do with the grid. We can look at it sort of as the cloud, as well as servicing all the legacy loads, and not invest a ton into the grid, the AC grid, upgrading it, but maybe start spending some money on converting some of it over to DC. And I know there's efforts that are underway to do that, even with the transmission lines to go to HVDC. There's experimentation going on in Europe to transform some of the medium voltage stuff as well over existing wiring. And sort of like when we went from horse and buggy to combustion engine cars and trucks, we already had the roads, and so we have to think of our wiring systems and such as the roads for electricity. We don't have to change those. So that's a big part of the infrastructure that doesn't need to be transformed, the physical asset of the towers and the lines and all that, although they can be problematic, and we'd love to have everything buried or somehow protected more from natural and man-made interruption. So, but that's the picture. So what Emera has done already, they did their pilot on an Air Force base in New Mexico called the Kirtland Air Force Base. And of course, the military is looking for resiliency and capability to operate, beyond the survival of the grid. And this was a relatively small pilot, but an interesting one. It had residential locations, these N1 through N6, I guess. N7 was a sort of commercial building, and N10, I think, was a laundromat or something like that. N8 was maybe a receiving office for people coming into the residential. So it was managing this whole residential section or one of the residential sections of transients coming onto the base. But it also it also happens to be the home of the Sandia Labs location for testing photovoltaics. And so down here where you see SNL, PSEL, that's the Sandia Labs solar farm there, if you will, for testing and experimentation. And so they couple that in as a community resource. What's interesting about it is, much like solar, it's not always available because obviously sometimes the engineering folks are using it for testing and whatever, but it couples into the grid as an extra resource. I'm sorry, was somebody asking a question? Sorry. So these are kind of the nodes that are in there, these buildings, which are these transient housing buildings. They all had solar put on them. It has vehicle charging, both fast and level 1 and 2 and 3 vehicle charging is coupled in there. This is a sort of a community battery pack over here that's sitting there. And of course, these are the solar panels, the farm solar panels from Sandia Labs. I just threw a couple of photographs in here just so you get a sense of the physical capability. But it's all interconnected again by DC links. This is a part of the GUI, and you can see that there's a number of ways of monitoring this. The homes and buildings themselves have graphical interfaces that tell them the status of things. I don't have the animation here, but I think I have a link that you can actually tie in and watch the power flows, and you'll see the power flows when the batteries are charging, when they're discharging, et cetera, what the capability of the whole system is doing, how much power it's using, and all that kind of stuff. In some ways, it's very basic, but some ways it's very advanced, because all this, once you set whatever your policies are about what kind of energy, green, whatever, that you want to use and couple in, it automatically transacts the power flows and the business. Now, at this time, they didn't have revenue metering engaged in this, but revenue metering is fairly straightforward. In fact, eMERGE has recently advanced an ANSI standard now, which is part of the C12 series of electric metering, revenue grade electric metering, that regulatory bodies can certify on. And that's for DC. So now you can buy and sell DC through a regulated, official weights and measures kind of certified metering capability. So that's an important thing. And right now they're about to commission a neighborhood, a residential development. I believe it's somewhere between 50 and 100 homes in a Florida development, where similarly all the homes will have solar. They each have a pedestal outside the home that manages the home as I'll call it a nanogrid, then coupling in community resources, and then ultimately coupling into the grid. And you can do that block by block or neighborhood section by neighborhood section, or however big you want your local networks or local grid swoops to be. Here's just a rendering of the kind of pedestal it sits on. You've probably all seen, whether it's the Tesla Powerwall kind of thing or other companies who have these battery pack and conversion modules that they're proposing to put into homes. So it's not surprising. That's sort of the personal computer sitting there, the personal power system, rather. The key, though, is how do we interconnect those into the grid, into a grid or network like the internet. Here's just a rendering of one of the community resources. You see some battery stacks there, maybe a hydrogen fuel cell or what have you, to supplement the neighborhood. So you got to remember that on buildings, of course, you don't always have equal photovoltaic or solar exposure and things like that, or wind presence and so on and so forth. So there's lots of variability out here at the very edge of these grids. But you can buffer all that or supplement it with these community resources and so on. So of course, if you're a utility, and this is all under the utilities domain, they own the solar panels, the nanogrid, and the community grid and community resources. But this could equally be privately owned and run by a third party or a community association. So I'm going to try to conclude, and then I'll ask if there are questions, and we can go back to any of these diagrams if you wish. The eMERGE strategy is sort of to help accelerate this, and because we believe that DC is a critical part of this evolution in terms of its ability to simplify the network. Now, a lot of people thought DC would be the efficiency and all that, and it has some efficiency benefits in certain areas. But more importantly is it can be digitally managed, and it is much simpler from an electronic standpoint, a physics of electronic standpoint, and easily coupled with the kind of digitalization strategies that we have. So we believe that and like I said, native DC resources that don't have to be, frequency controlled and things like that, and phase matched and so on. So what eMERGE is trying to do is fill in the gap that has been left regarding DC. So we have a number of efforts working on what we call a vanguard approach. So it's not a comprehensive approach of standardization, but a leading edge approach to standardization. We're actually trying to standardize some basics. I'll call it the kind of simple view of the standard, and I'm sure they'll get more complex as we go along. But to get things started in the right direction. And hopefully by making them very streamlined, very simple, it will do two things. One, it'll speed up the process because we don't have to be comprehensive. Sometimes standards will take 3 to 5 years because they try to, cross every T and dot every I. The other part is that they can help avoid the kind of delays that are incumbent when people do things differently, and then you have stranded capability, or you have investments in branches of the tree that no longer connect to the trunk, if you will. So we think it'll overcome a lot of that slowness that normally associated with standardization. Of course, the proof is in the pudding. We've created a couple standards already. We have one for beginnings of commercial building standard, mostly dealing with interior loads and so on, but now we're doing the entire premise kind of thing. It's in revision right now. We have a standard for data centers and central office telecom, what we call the ICT. And we have an ANSI recognized standard for metering, which is critical. But the icing on the cake is we're not stopping there. We're actually developing. We have a group that's working on the what you would call the grid of grids interconnect, trying to find the analogous equal to what we use the Ethernet for information coupling. So that's kind of what we're doing. I just threw in this other slide. Oh, and just the part on the right, historically we started out with DC. A lot of people, if you look at this little, whoops, am I on the right side? Yeah, on the left side, the shaded portion, but the left picture there, which is kind of small, but it says thousands of small individual local generation units, that part. There are almost well over 1 million, but some people had guesstimated about 2 million technically isolated microgrids in the United States between 1917 and 1945. And they were almost all of them were in rural areas, mostly on farms. But they did include a generation capability. The generator had an auto start capability, which was invented by the way, Charles Kettering. Later, many of you know Kettering, Sloan Kettering cancer, but he became R&D director of General Motors. But he invented or at least he's credited for the invention for the electric start and for the droop controller. So what he did was he would start that generator, made the system such that it would start the generator when the voltage drooped from the battery stack, which you see along the wall there. Glass jar, lead acid batteries. Actually formed a company called Exide, which still exists, I think, making batteries. And so you'd have batteries. The early systems were 32-volt systems, so it's a stack up of 1.5-volt cells and such. Later on, I think they went as high as 100 volts, but it was all local. So it really was just the personal computer equivalent, no networking. So farms were not networked together or anything like that. So each farm had its own thing. But they also had they brought in washing machines and irons and corn huskers and automated, hubs like you'd have on a tractor to process the farm's harvest and all that kind of stuff. So it made a huge difference in farming between, prior to and leading up to World War II. So we think that that's, in a way, not going to come all the way back, but here we are over on the total right, where we have the centralized AC, which is great to stretch lines out to the rural areas, but never thinking that they could couple the DC because there was no voltage transformation capability with DC at the time. It didn't come later until we got to transistors, and particularly power transistors and IGBT technology. So it was no way to make it into a network at the time. They were literally more like the typewriter, I guess, than they were the personal computer. But we swung all the way over to everything was centralized, and I think we're on the way back to the middle somewhere. And so I think that most of this century will be this hybridization. There's still a lot of time value in the current grid and AC, fixed frequency AC. And by the way, eMERGE and particularly myself, I am not against AC whatsoever. But what I do see is a proper use of it, and particularly the AC that is more and more useful as we go along is variable frequency AC, not fixed frequency AC. So in variable frequency AC, there's a ton of things we can do, including I benefit from it because I do induction. My cooking is done with induction cooking, and we need to vary the frequency. But I think most of us recognize that whether it's appliance motors and vehicle motors and all that, that there's still a great value in AC if we can articulate its frequency by starting out with a DC signal or DC power. So I think we're on our way to back to the middle. How long it's going to take? Probably another to get to the 80% on the S curve. It's probably through at least 2030, maybe 2040 or something like that. But it's happening pretty quickly. As I said, the acceleration factor of all those, the nexus of all those technologies we just talked about, some of which will continue on. If you talk about graphene and you talk about digital power, meaning the DC-based digital kind of power, Those are really down at the bottom of the S curve. So there's a while before they even become practical in many cases. Although I guess digital electricity is now being used at the lower voltages and starting to be deployed into the field. So maybe it's not so far off. I wanted to throw this up here because a lot of what we do at eMERGE is to try to figure out, how do you connect things together, whether it's an individual microgrid or one microgrid to another. But when you do that, you just simply look at the microgrid as just another resource at the front end of this, or a load, or a combination of resource and load. But this is just a diagram that we sometimes use with our committees to kind of just say there's a section of inputs, there's storage, there's outputs, and there's some sort of management or conversion. I'll call it the processing of electricity. So it's very similar to the concept of the modern computer. And of course, we look at voltages, and a lot of these voltages are here because they're trying to match legacy use of different things. I don't know that we would have automatically picked 48 volts or 24 volts or 5 volts for USB or whatever on our own, but they're there, so we have to accommodate them, at least for a time, until there's a further simplification. Actually, I think that the fixed voltage thing will go away eventually, because when we have digital digital power, we'll be able to time domain multiplex different voltages on the same wire or same system. So I think digital multiplexing of power will be something that will replace a lot of this kind of sea of voltages that need to be dealt with. I call it the anti-volt system to simplify the thought. Again, I think this largely brings to bear, again, the development of renewable resources, hydrogen, solar, wind, all that kind of stuff, and probably many more to come, maybe atmospheric harvesting and so on. And the tremendous gains that we're experiencing in power electronics all come to bear. And then, of course, the use of power in everything from vehicles to indoor farming, vertical farming, hydroponics. Recently we have a member that's very involved in agricultural use, and some of the power densities in the vertical farm are very similar to a data center, if you can believe that. So there's a lot of power going into a very small space. Their biggest problem is the utilities cannot deliver that much power, so they have to wait sometimes for years. And that industry, well, it started out with marijuana growers, but now it's into cash crop produce, and even was it Whole Foods and so on are prototyping vertical farms within their stores. So that'll be interesting. You pick your own lettuce when you're shopping. In any case, on the other side is the whole data world and the ICT world. And many of you are probably more expert at what's happening there than I am, but the whole idea of being able to ledger transactions, whether it's blockchain or other systems, and the whole IoT and artificial intelligence and the cloud concepts and so on and so forth. So there's so much that's coming into existence that's going to make this. Now, it also can make it confusing. So that's, some of our role, if you want to consider, if you have a role in this, is to sort out this kind of chaotic appearing nexus of technologies and make sense out of it and see how it really should be put together. Otherwise, it'll take longer. So we have a technical standards. We do two things in eMERGE. One is to try to help fill in the gaps in technical, at least early technical standards, and the other one is to promote the whole notion of a grid of grids. Okay, so at the top of our hierarchy and thinking is the grid of grids, and we do have a committee that's looking at most specifically how do you couple at those higher levels, even up into the medium voltage. Probably not high voltage DC, because we think most of the action is going to be downstream of substations, whether they're privately owned or utility operated. And then a lot of people argue with this approach, but we decided to develop individual standards, the standard for all these vertical industry use verticals, I'll call them. Probably 85% of what happens in these verticals is very similar. from a standard standpoint, but we felt that we should identify uses because we felt that there were nuances in the way you would configure things, for example, between a residence and a data center or a commercial building, or for that matter, an EV fleet charging system or a military base. So we're trying to draw in the sort of the stakeholders from these different verticals to opine on what their needs are. Because at the end of the day, the value of all this is largely a better accommodation, identification and accommodation of needs. Because that's where the value comes from, by satisfying needs. So if we can identify the needs in a much clearer way and then devise the technical standardization that accommodates those needs in the best way, we will have the most value creation in order to pay for the transformation, which eventually will, like the internet, maybe at the beginning you couldn't justify personal computers and all the gear that you might have had, but today we buy $1,000 cell phones without blinking an eye because of the value that they create. So that's the end thing. And there are also special devices, obviously, that need to be looked at that are different with DC. We've addressed the metering one, at least initially, but there are other devices there. We're working on the AC-DC hybrid input, so that appliances, hopefully in the future that you buy, will be able to be fed with either AC or DC power. DC protection, circuit protection, you can do it today. It's a little bit more expensive than it should be, but we're working on standards and ways of doing that that'll bring the cost of that down. And last but not least is standardizing around DC connectors. Much like information system connectors, there are hundreds out there. Fortunately, in information system, we're starting to standardize on fewer and fewer connections, physical connectors. I think USB is at the low end is making a big run on things, and so that's part of the standardization effort. At this point, I'll ask for questions. I know I went on quite long, but
this has been fascinating, Brian. Thank you so much. I think we have some questions. Let's start from chat. I am unmuted, yeah, right, okay. So Subir had first question. Subir, you want to state your question?
Yeah, hello, Dr. Brian. This was fascinating talk that you have. Yes. I have got a couple of questions here. The first one was that, conventional power plants exploit the economy of scale, so basically that given that the larger the plant size is, the prices of power becomes the fixed cost component of the power gets quite a lot cheaper, right? Yeah. With the DERs and all, they are of very small size, although they are renewable based, but so if they are given their small size, they are inherently expensive, right? What's your thought on that? And the second question is also like, you talked about the sub-Saharan region that is kind of in the center of the globe, and that has a lot of solar photovoltaic penetration, like right, global horizontal irradiation kind of stuff. But the problem is they have that's the nightmarish region from the supply chain point of view. And I have seen quite a lot of YouTube videos talking about all these things. What are your thoughts on that?
Okay, take the first one. Whenever I think about the how cost is going to be covered, I try to make a comparison with the information systems. When I first worked in a company and I was doing production control, which was at the time manually charted, believe it or not even on a computer, we computerized it. I remember the Winchester disk drive.
Benjamin Walk-in closet.
To hold the memory for my production information was tens of thousands of dollars, and it was almost you couldn't justify what I was doing because the price of the memory alone was just incredible. Today, I can get the same memory on my personal computer on the little thumb drive, right? Or even in the solid state memory, which I don't know if I have mine here, but I have it in my suitcase.
I see.
But you have it in small things. So the cost is going to continue to come down. Now,
Economy of scale again, yes.
yeah, it's basic economics, and I worked for a long time in communications, and as communications spread, the cost of things came down. But when automotive came in and started using electronics, and the first one was, believe it or not, electronic radio, but then it was an electronic engine control, electronic braking systems, and so on. And look at the car today; it's more electronic than it is mechanical, I think. The cost, just the volume of those applications brought the cost of semiconductors and everything else that was involved down. So I don't think for a minute that even renewable energy, including photovoltaics, is done on their cost curve. I think they're still at best in the early part of their cost curve, and it will continue to come down. Remembering that they haven't even employed materials like graphene yet, and things like that can just radically change the whole complexion of cost in electricity. So I think, while you're right that, and this is the timing issue, how fast do things happen? Well, it's based on that economic curve more than the technology curve. The technology curve is already there. We know what we think that progression is likely to be. The question is, how fast will it get into volume production? Thank God, in a way, for automotive again, because automotive is going to come along and provide a tremendous market for battery storage and other devices that will hopefully make cars economic. I know I have a Ford Lightning on order, and I can't justify the cost for it, but emotionally, I'm bought in, But that's the kind of thinking. They're going to be early adopters, and they're going to pay more because they think they need it or want it. But I think the cost curve is going to take care of that. Your second question was about had to do with underdeveloped portions of the world. Is that what? Could you repeat that part? I'm sorry.
Sub-Saharan region, and transportation or any supply chain is a nightmare, right? Like, you need to bring all this equipments over there. You need to build a power plant, not just erect the PV, because on the top of building the PVs, there are regular maintenance and all.
Yeah. Well, initially, and I know the World Bank had started to fund some projects in Africa. Unfortunately, a lot of the early projects went to implementing traditional grid. And I shudder when I see that, because I say, well, there's some money that is going to get stranded. It was in Ghana, as a matter of fact. They got a tremendous loan to extend their grid. And if you looked at it statistically, I went to a conference in Africa where 80% of the homes in Ghana are connected to the grid. And you say, wow, that's really tremendous. And the fellow from the utility said, well, wait a second, not so much, because only half of those connected people can afford to buy the electricity. So therefore, the cost actually of a kilowatt hour went up as a result. Now they have to pay off the loan, but the price went up and their customer consumption actually went down. And so people are trying to, figure out that. I said, if only they had put solar panels on all those homes and used it as a bidirectional feeder network, because most of the homes want power at night and most of the cities want power during the day. And that was the dilemma. And if they'd done that and made that kind of investment, a bidirectional, and we would say DC coupled, grid, that investment would have much more sustainability. So I don't know what the timing exactly is, but the more times we make that kind of a mistake and don't look at the systemic sustainability of what we're doing, that we're going to continue to slow down the transformation.
Thank you very much. I think Hartmut Schmeck from Germany. Hartmut, you have a question you want to state?
Yes. Okay. Thank you, Brian, for this very visionary and enthusiastic talk. Very interesting. As we all know, the Internet of Data is based on the fundamental concept of packet-based information exchange. Mm-hmm. You briefly mentioned that you have an idea of using energy packets. So have you actually implemented and run is an electricity system that is based on energy packets. Like if you tell that this idea to some power engineer, they will say, "You are kidding. Like electricity is not running with packets. That's not possible." But nevertheless, there are projects trying to do that. So have you done that actually?
Yeah. The answer is yes, but with some caveats. One is I have personally done it in my lab when I was working at Armstrong. So we ran network with multiple voltages on the same grid. We were actually using ceiling grid of all things, you know, the grid that holds the tiles in a commercial ceiling up. So that had a grid, a literal physical grid of power, but we had devices that needed different voltages. So the way to solve that was to put a buffer or battery at each device so that we could time domain multiplex the bursts of power, I'm going to call them. I don't know that I will call them packets yet, but they're bursts of power. So we would feed, 48 volts for a while. And so all the 48 volt devices would store up whatever they needed for a time. And then we'd feed 12 volt or we feed 100 volt or whatever. So we could feed different voltages, but the devices would either connect or disconnect if they had the proper voltage, if they saw the proper voltage on the line. So that's one way of doing it. And that's more bursts or switching from different voltages over time. Right now, there is a technology. You can look up a company called Volt Server. And actually, Cisco is going to announce a product, I think, later this year that is a true packetized power. They start out principally in the low voltage range, under 1500 volts. I know the Volt Server systems are 350 volt. They are a fixed voltage and they are a continuous packet approach, but they do put a header on each pulse. And that header right now is not used for addressability, but used for safety detection. So what they do is they put a header on it that has a distinct profile, and then they look at the receiving end, whether that header has been corrupted. If the header has been corrupted, the receiver tells the transmitting point to shut off as a safety means. Now, what does that give you? And I've done this. Maybe you'll probably think me foolish after I say what I did. 350 volt line, 5 amps, and I could grab it with my bare hand, because the system would react to my corruption of those packets, if you will, or those headers, so fast that there wasn't enough electricity transmitted to my body to do any damage. I could just barely feel that I even did it, and I didn't even know whether it was because I was physically touching, the sense of touch, or whether I actually had any electricity transmitted. But it shut down in literally microseconds, maybe even nanoseconds. I forget what the time domain was, but it's so. I think we're right there. I think when maybe Cisco announces its product, you'll see maybe even more of that. But I know it's in use. The Mercedes-Benz Stadium in Atlanta, Georgia, is their 5G system is all powered by digital power, this kind of power. So done by Volt Server. So there are people doing it.
That's fascinating. We have one more question, and then we will finish formal part because we are running out of time. Koti, ready? Would you like to state your question, please?
Yes. Thank you, Mr. Brian, for a beautiful and wonderful talk and future expectations. May I know, I have two questions. One is this global grid of grids, present scenario of entire world where some disturbances are going on. Is it safe to have global grid of grids? If yes, how to protect during disturbance at one border? Please clarify. And I'm very happy to see the image or illustration by you of nano grid different voltages. I am very happy and to see that. Yeah. Please clarify my doubts. Thank you. Thank you.
I think the fundamental elements of protection in any system are two or three principal things. One is disaggregation, so that if somebody's going to try to disrupt something, you want to make it so that they have to go to many points in order to achieve their end, whether that's natural disruption or man-made. I remember I was living in rural Pennsylvania for a while, essentially in farm area, and I had didn't have municipal water. I had a well water. And everybody used to say, "How that's so old and archaic, and you have to pump your own water and all this kind of stuff." Of course, it was a very modern well. It was down 300 feet. It was a great water, by the way. It was probably the best water I've had in my any place I lived. And so one day, it was announced that there was a threat, a terrorist threat, on contaminating the local municipal water reservoir. And I said, I hate to put it this way, but I thought of buying a gun at that point, because I knew, not to put to my head, but I knew that the people around me would be so desperate for potable water that they might try to take over my house and throw my family out so they could get to my well. My point is that it's much easier to corrupt systems when they're hard connected in a physical way that makes them, an easy big target. And that, again, I say, whether that's weather, EMP, terrorist threats, whatever, disaggregation is a fundamental strategy to protection. The other is to have fast reaction. We have a lot of that already. The communication systems we have, and assumedly we're trying to make progress on those communication systems to make them less corruptible. I see I got a warning here, so I just have to deal with that. And so the information system that we have is sort of a early warning system, and the ability, especially with a DC system where coming on and off the grid is easier and less disruptive, means that we can isolate, given enough warning, and that could be nanoseconds, that we can isolate problems, so that an attack on one node or multi-nodes in the system don't corrupt the rest of the system. We don't have that today, as you know. So I think that fundamentally, that ability to detect corruption and then to isolate it very quickly is the other main thing. Other than in military applications, I don't know that it's affordable to harden a system such that you could avoid all corruption, or most corruption. But most of the so-called energy network that we're talking about is not going to be for the military. It's going to be, for normal living, hopefully. Hopefully we can maybe even reduce the amount we need for the military over time. And I say that not tongue in cheek, because I do believe that a lot of the inequities around the world are based on the disproportionate access to energy, and as we're kind of seeing even today, right? Unfortunately, so I think this grid of grids, the worldwide global grid of grids, much like the internet, will level the playing field, even in a social political nature. So I don't know if that fully answers your question, but those are the, that would be my answer: disaggregation and early response, and the ability to isolate faults.
Brian, this is great. I don't want to stop yet. Let's just ask Sheila again from Michigan. Can you just ask your question before we close?
Mm-hmm. Yeah. Yeah, Maria. Yeah, this is Sijia. I just joined Leeds from University of Michigan. My question is that, in your opinion, would this transformation to future grids of grid a natural evolvement, or do you think any particular stakeholders need to make an effort to such a revolution? Yeah, basically, how do we reach the future you envisioned? Thank you.
Okay. Well, that's a very complex question. I'm going to go to my close. I'm going to go to my closing slide. And I'll come back, because I want to show you one more thing if you have time. So you're kind of asking, what do we do? And you notice I crossed out we, and I crossed out can here. It's what you and I, and each one of us as individuals, will do to change this fate of the world. And I do think that we are just at the beginning of the ability to change the fate of the world in a certain sense. We know, we've learned the hard way. A lot of it's based on energy and energy equity. If we don't create a system that solves that particular paradigm in a positive way, I'm afraid that we will be at the end shortly, whether it's climate change or social war or what have you. So we do have to do this. Now the question is, how can people help? I think all stakeholders need to help. I am a little bit, and I've always been a little bit jaundiced of people who try to help, but try to incentivize things in the wrong direction. I gave the example of the World Bank, but and I don't mean to pick on the World Bank because I think they do wonderful work, but to put out incentives that are wrong are as damaging as they are helpful in many cases. So I remember, and I thought President Obama was a decent president and all, but he put out the shovel-ready kind of mentality. One of the results of that was for us to switch largely from traditional fluorescent to compact fluorescent and smaller tubes. I don't know if and this is a kind of a simple one, but lighting at the time was earmarked as being a third or more of all the electricity used in buildings and so on and so forth. So it had a bad name. Have to reduce the amount of electricity used for lighting. So let's get better fluorescent. Companies spent inordinate amount of money to improve fluorescent lighting. They went to narrower tubes, compact fluorescent light bulbs, etc. Within 5 years, the LED technology replaced, or was in the position to replace, almost all fluorescent lighting. Now, people might argue with that, but by and large, it's true. And for sure, if you were investing in an upgraded system based on government incentives for supplementing your expense in putting in those new systems of fluorescent, and had to amortize those over either 7 to, in some cases in the United States, over 29 years, LEDs were half the time of the shortest amortization cycle of the fluorescent lighting investment. And so not only did we have a stranded asset if we tore that out, but we also, for those who couldn't afford to tear it out and reinvest in LEDs, they suffered with higher energy use until their fluorescent bulbs finally gave up the ghost and died. So I am very skeptical of incentives that are too specific. I'd rather see money and incentives go into research, academic research, to supplement loans, real loans to companies, commercial firms, not necessary to incentivize a particular technology or what have you.
Yeah, great. Thank you. I think, Hartmut, you have one more question, right?
Well, not a question, just a remark. Some years ago, like in 2016, Xi Jinping, the Chinese leader, he suggested a globally interconnected electricity system, the global energy internet. So this idea has some tradition already, and they are heavily working on that. Yeah, they really formed committees for that and things like that.
Yeah, actually, they were one of the early adopters of a lot of DC, their data centers. They actually have 2 competing standards of voltage. It's one of the criteria that's critical in DC systems, at least until we go to what I call anti-volt system, is to pick voltages. So your bus voltage in particular, not necessarily equipment utilization voltage, but a bus voltage where you're coupling things. Gets to be critical, or a strategy around that. If it's a range, fine. If it's a floating bus, that's fine. But you still have to establish ranges, particularly if you're going to use droop control in that. So all of that is critical. But you're right. China, they had 2 standards. I think that we have emerged basically at one of our voltages we espouse on a bus is 380 volts. It's for data centers and stuff. And China has that, as well as Japan. But they also have a 240 volt standard. And it had to do with, componentry and what equipment they had. And so a lot of times these voltages and other judgments are made based on what available technology in the component world or what safety certifications are available. We arbitrarily call 15 or 1600 volts, depending upon where you are in the world, as low voltage. Under that is low voltage, and then there's a medium voltage range, and then there's a high voltage range. Those are kind of arbitrary barriers, but they set out then to define what are the safety requirements in each of those domains, and so on.
This has been actually fascinating, Brian. I want to close with one sort of academic question on my side, and I've seen several academics who came and came and left because of the time constraints, but I think it's been on our mind in academia. If you do this, let's say you want to do this grid of grids in Puerto Rico, where there's a lot of solar, right? And you want to replace all the. How do we know it's going to work? What are the other open questions that academia should deal with, so that we ensure when you start putting these things in a plug and play way that actually would work? And so I think there is a little bit of a disconnect between saying, okay, I just put this in between the different black boxes and I know that it's going to work. I think it's going to take a little bit more in terms of getting from here to there when you interconnect these microgrids. Can you comment a little bit on that R&D challenge?
Sure. I strongly believe in engaging the academic world in this whole effort. In eMERGE, of course, we have academic memberships. They're non-fee based, so they're basically a reciprocal liaison membership where you can participate in the development of these standards. And again, they're vanguard standards, so they're early standards and really critical that the basic physics of what we're doing have to work. As a result, what we've seen is some of the universities that we've been dealing with have then set out to do two things. One is to do pilot projects in their own R&D environments and set up pilot demonstrations and experimentations, both for their for academic reasons, but also for student development reasons. Students like to engage in a lot of this. So it's very critical, and I'm a big on pro education involvement here. The other thing is that I see universities then need to engage the commercial firms, and most of the successful pilots that I've seen are an academic commercial partnership of some sort. You can do it with one company or you can do it with many. But I think it's important in the academic world that you do have some sort of ongoing relationship with the commercial world. And of course, government. You can always get engagements or involvements with the national labs. We also have most of the national labs that are working in this electricity domain. NREL and Berkeley and Sandia Labs are all eMERGE, have eMERGE liaisons. So many of them, in fact, most of them, we usually have somebody from the labs attending almost every one of our committee meetings. So there's that connection. The one good thing, if you choose to use eMERGE as sort of a locus, and again, for the academics, it doesn't cost you anything other than to attend meetings and stuff like that. But it is also, as I like to call it, is an intersection of thinkers on the subject, so that you start to rub elbows with the academics, the commercial people, the standards people, and so on. Because we need to have end users. So we need to have, OEMs are a big part of what we do, original equipment manufacturers, the Eatons and the Ciscos and so on. So we invite you to that. Hopefully you if you're interested, you can either drop me a line or whatever, and we'll start that process. I did want to mention, so I hope that answers the question as to what can happen. By the way, in residential right now, I think Purdue has a Purdue House. I don't know if you've seen that project. And out of New Mexico, in New Mexico State, they are doing a pilot of a microgrid, DC microgrid neighborhood. So
nice.
the universities have at different levels, some focus more on the individual technologies like hydrogen or solar or whatever, batteries and so on. But more and more I see some of the academic institutions looking at the whole system. I know Pittsburgh, University of Pittsburgh, we have they have membership with us, and they have a medium and low voltage lab, which is pretty expensive, but they had the local utility involvement so they provide services to the local utility for some research for them, as well as I think they're the home base for Eaton Corporation. So they have some funding coming into their labs on that basis.
This is great. Thank you very much. I think, unfortunately, we have to finish, but it's been fascinating presentation, Brian. Very much. Thank you.
I did want to very quickly mention that we'll be at the Anaheim, California meeting. It's called RE Plus North American Smart Energy Week. It's in September. We'll be demonstrating some of these technologies based on members coming and demonstrating. We provide a platform for that at the trade show. So if you can, it will be in the infrastructure section of that show. That's, some of you may know it as SPI or Energy Storage International or Hydrogen International, whatever, but that's all under one roof in this Energy Week, North American Smart Energy Week. And we sort of manage for them the infrastructure section, which is largely, microgrids and the grid grids.
Great. Thank you very much. Thank you, everybody, for staying this long.
Yeah. Thank you. Thank you.